Okay, Bismillah ar-Rahman ar-Rahim. This is the second part of the data warehousing lecture. We're going to start our lecture by discussing the OLAP operations, typical OLAP operations. And I'm gonna discuss this and demonstrate this using some examples. First of all, the roll-up operation. If we look at just one second, I'll use a pointer. So if we look at the data cube here, we have a data cube here, and this data cube consists of 3 dimensions: location, item, and time. Location in terms of cities, time as quarters, and items. A roll-up operation, roll up on location from cities to countries, transforms the data cube from being detailed into a generalized form. So instead of having the data in terms of city, we're going to have it in terms of countries. Performing a dice operation on this data cube by specifying the values of location to be Toronto or Vancouver, and time to be Q1 or Q2, and item to be home entertainment or computer, will result in a smaller cube showing only the data based on these values. Another operation, which is the drill down operation, the same data cube containing locations, items, and times. Time here is in terms of quarter, Q1, Q2, Q3. So if we drill down on time from quarters to months, the data will be showing to be monthly instead of being quarters. So it's going to be showing in a monthly base. So this is a drill down operation. A slice operation on the same data cube based on time to be Q1, which means that only the data of the first quarter of the year is shown, will have location or show us location in terms of city and items, and it will give us data based on that. Applying a pivot operation on the same section of the data will reverse the X and Y axis of the cube. Now, when we want to think about a data warehouse, we will be thinking or having multiple views of a data warehouse based on or depending on our point of view or our interest or our function regarding a data warehouse. So if I am a business owner, I'll be more interested about what kind of business queries the data warehouse will provide. If I am a data warehouse designer, I'll be thinking about the fact tables, the dimensions that construct the data warehouse, what kind of measures are we including? A top-down view of the data warehouse will think of what relevant information to include in the data warehouse. And a data source view will think about how to capture, store, and manage the information into the data warehouse. When designing a data warehouse, the data warehouse design process can be either a top-down or a bottom-up approach, depending on expertise, or it sometimes can be a combination of both. A top-down approach of design starts by having an overall design and will be applying this design in order to construct the data warehouse. A bottom-up approach will start using experiments, by using prototypes, by using subsections of the data in order to create and to come up with an overall design. Thinking about it in software engineering point of view, it's either a waterfall model or a spiral model, where a waterfall model is structured, systematic, and we cannot really move to the other step until we are finished with the current step, and there is no moving back. A spiral approach means that we will be constructing the data warehouse using a subset of the data and then adding more data as we move on until we finally finish into using an overall plan. When we are developing a data warehouse, the recommended approach is that, first of all, we should have a corporate data model, a highly, a very well-defined corporate data model should be used in order to create data marts, and we explain data marts as subsections of the data warehouse with special interest groups. Let's say data mart for salespeople, data mart for marketing people. And these data marts will be constructed in a distributed data mart structure. Using the corporate data model, we will be constructing the enterprise data warehouse. Using the data warehouse along with the data mart, distributed data mart, we end up with a multi-tier data warehouse as explained earlier. Data warehouse is useful in information processing, analytical processing, and in data mining. In information and processing, it provides us with basic statistics, reporting techniques, cross-tabulations, tables, charts, visualizations, graphs, etc. Analytical processing are the all-up operations that we just discussed, including the slice and dice, drilling down, and rolling up and pivoting. Data mining means that we apply data mining algorithms in order to discover knowledge from hidden pattern. Why are we, or how are we able to apply data mining, analytical data mining on data warehouse? First of all, the data warehouse contains high quality data, which is integrated, consistent, and cleaned. It also facilitates or provides multiple facilities that are incorporated within the data warehouse that allows us to apply data mining algorithms. The most important task regarding data warehousing computations is efficiency. Efficiency is the idea of making use of the data with the least cost in terms of computation time, in terms of space. Efficient data cube computation can be approached or can be supported using multiple approaches. The first approach that we're going to discuss here is materialization of data cube. A data cube can be either fully materialized, partially materialized, or no materialization. No materialization means that we will be saving a data cube in the form of a design. The actual measure that the data cube is calculating is not calculated. For instance, in the data cube where we have item, location, and time, we're not calculating the sales in dollars. This is the no materialization approach. The partial materialization, or sorry, the full materialization approach means that for all data cubes defined in a data warehouse, we are actually calculating the measures. So we will have the sum of sales calculated and saved, the, for example, average sales calculated and saved, the count of sale will be calculated and saved, etc. Partial materialization means that some of the cubes that I have will be materialized, calculated, and stored. Others that are not frequently accessed are not materialized. So how do we determine or which to materialize and which not? This is based on the size of data, the sharing of data, how frequently we access data, and other factors. Now, we want to talk about the lattice representation of the cuboid, which means that we'll have 0D, 1D, 2D, 3D, 4D, based on the number of dimensions we have. Here we have 4 dimensions. The 0D will have all, and then the 1D will have supplier, location, item, and time, and then the 2D will have pairs, and the 3D will have threes, and then we have finally the 4D, which is all of them. We continue with the efficient data cube computation, and here we're talking about the SQL aggregation functions. If we think of a multi-dimensional analysis of data or representation of data, we're actually thinking of aggregation functions, sum, average, count, etc. This means that we can have also some group bys. These group bys, when we think about them in the data cube, we're actually thinking about possible groupings where we can retrieve values of. For example, here we have the data cube of all electronics having 3 dimensions: city, time, city, item, and year, along with sales in dollars as a measure. So if we want to run some queries on this data, we can have multiple number of groupings, multiple options of groupings. So we can calculate the sum of sales grouping by city and item. And in this case, we will have all the cities: Vancouver, Toronto, New York, and Chicago. And for each one of them, we're going to calculate the sales for TV, home entertainment, mobile or computer. Again, for Toronto, TV, home entertainment, mobile or computer. Again, for Chicago, TV, home entertainment, mobile or computer. And for each one of them, we'll be calculating their sales. Compute the sum of sales grouping by city. It means that we'll be calculating the sales in Vancouver, regardless of item, the sales in Toronto, regardless of item, the sales in New York, regardless of the item, and the sales in Chicago, regardless of the item. Compute the sum of sales grouping by item. It means that we'll be calculating sales for home entertainment regarding the city. We'll be calculating for TV regarding the city, and we're going to calculate regarding the mobile and computer. The number of possible group bys that we can have is represented by 2 to the power 3. So the formula is actually calculated based on the number of dimensions we have. So if we have 3 dimensions, we have 2 to the power 3, which is 8 possible group bys. And here are the group bys. All of the items together: city and item, city and years, item and year, and then city, item, year, and then no grouping. So based on this, these number or these dimensions will represent the number of possible group by operations that we can compute using the compute operation. However, if we want to compute all the possible combinations, all 8 group bys, in this case, we'll be using the cube operator or cube by operator. When we say cube by operator, item, city, and year, it will repeat the same order 8 times, because we already said that we will have 8 possible group bys. Another aspect of efficiency is using indexes, and an index is just like an index of a book. It allows me to quickly access data in order to retrieve it. An index can be created based on a particular column. Each value in the column will have a bit vector because bit operations are fast. The length of the vid vector will equal the number of records in the base table. And when we want to represent the index of a certain column, so for index on region, we will have the same number of records. And then we will give 1 to the value of the original attribute in the base table. So for customer 1, the region is Asia. So it will have 1 in Asia and zeros for the rest. For customer 2, the region is Europe. So we'll have 1 for Europe and zeros for the rest. The customer 4, it's America. So we'll have zeros for the rest and 1 for America. This is also the same idea, the same index on the type column. Now, this approach or this indexing is not suitable for high cardinality domains, meaning the domains that have too many distinct values. However, there is an upgrade that allows for incorporating high cardinality columns. Indices can be joined for providing ease of access. So if we want to join location and item based on the sales fact table, we will be using the index number that points to the values of the location and item based on which one. And in this way, we will be able to identify the sales key for each of the values. So for location, these are the sales key. For item, these are the same of the sales key. And joining the table will linking the location and sales and item to sales will present us with this record. Another efficiency idea is that once we want to retrieve data, it's better to use the most relevant cuboid that will give me as much as possible the data that I need in order to answer my question. More data means wasted computational time. And if we need the precise data, it's better to be as specific as possible. So in the case here, if we have brand, province, or state, and we want the data of 2004 only, then we'll be looking at this option, which allows me specified year data, compared to, for example, this option here. It specifies all years, item names, and cities. Now, a last subject we're going to talk about is the attribute-oriented induction. Attribute-oriented induction was introduced in 1989, and it is applied on data, either categorical or non-categorical. Attribute-oriented induction allows us to collect task-relevant data to generate a initial relation, and using a relational database query, we have a subset of the data that we need. After that, we perform generalization either by removing attributes or generalizing attributes. And then we apply aggregations by merging identical records and then adding counts. After that, we present our knowledge for users in terms of visualization, rules, or graphs. Attribute-oriented induction, which is this is an example. We want to describe the general characteristics of graduate students in the university database. General characteristics can be age range, GPAs, gender, height, any kind of characteristic. And graduate students are students who are in master's or PhD level. The first step is that we fetch the data that we need in order to perform the generalization. We fetch the name, gender, major, birth date, birthplace, birth date, residence, phone number, and GPA from student, where the student status is master's, MBA, or PhD. And then we perform AOI, and we're going to explain that in a minute. And then we'll be presenting the results in generalized relation, cross-tabulation, or rule forms. This is the example here. Performing AOI here means that we'll be removing or generalizing some attributes. So we'll be removing the name attribute and the phone number attribute because they are not generalizable. We cannot generalize them. They are two distinct values. For gender, we'll leave it as it is. For major, instead of having the detailed major, we defined 3 categories: science, engineering, or business. After that, the birthplace, we only specify the country, and here we have 2 values, Canada or foreign. The birth date, will be calculating the age and the age range. For the residence, we're only taking the city. And for the GPA, we're transforming it into excellent, very good, good, and etc. This means that we will end up with records that are similar. These records will be combined in one record, and their count will be provided. So male science Canada 20 to 25, Richmond, very good. This means that we have 16 records like this. Female science foreign 25 to 30, Burnaby, excellent 22. We have 22 students with these characteristics, and then we choose and mix and match, presenting the data as we wish. The principles of AOI, first of all, it's task data focusing, meaning that it will focus on task relevant data. We remove attributes. If the attribute has large set of distinct values, then we remove the attribute. We generalize the attribute in order to minimize the number of values. We need to control the number of attributes to be between 2 to 8. And we need to control the number of the resulting generalized relation to be in a concise and acceptable size, not too small, not too big. The steps for the AOI, first of all, we have the initial relation, where we retrieve the task relevant data. Pre-generalization, where we determine our generalization plan. Prime generalization, where we perform the generalization plan and then calculate our counts, and after that, presentation. The data can be presented in various forms. One form is rule-based representation. So here, if we have grad X and male X, means that the birth region of X equal Canada, 53%, and birth region of X equal foreign, 47%. AOI is also used to compare 2 classes. For instance, if we want to compare graduate students to undergraduate students, we will be performing the same steps and comparing them using the various features that we have. Similarity between AOI and cube-based OLAP, they are very similar in what they present and their results. The main difference is in the process itself. So AOI, or concept description, will actually have to retrieve data every time, perform cleaning and pre-processing, and then constructing or presenting the data. However, OLAP is actually systematically pre-processed, where data is ready beforehand and can be accessed for analysis at any time. This is it regarding data warehousing. It's a multi-dimensional model of data warehouse. We spoke about data cubes consisting of dimensions and measures. We spoke about 3 types of schema: star, snowflake, or fact consultation. OLAP operations, including drilling, rolling, slicing, dicing, and pivoting. The data warehouse as architecture, design, and usage. We spoke that it's a multi-tiered architecture. We use it for business analysis and provide support decision making. We use it for information processing, analytical processing, and data mining. Implementing the data warehouse means that we want to efficiently compute data cubes using materialization, full, partial, or no materialization. Indexing of OLAP using bit indexes and joining these indexes. And also OLAP query processing using the compute and compute cube. And finally, we have data generalization using attribute-oriented induction. Thank you very much.